Emergency Shutdown System, modernized design and functionality. The Emergency Shutdown System ESD is a mission-critical safety layer designed to autonomously isolate, depressurize, or halt operations in response to hazardous conditions, protecting life, assets, and the environment. Modern ESD systems are engineered to Safety Integrity Level SIL3 or higher, conforming to IEC 61508-61511, and integrated seamlessly within the larger control ecosystem while maintaining strict functional independence. Core objectives and design principles. Safety-first architecture. The system guarantees rapid execution of predefined protective actions during abnormal events. Its primary purpose is to safeguard personnel, contain hazardous materials, and prevent escalation by triggering fast, deterministic shutdowns. Digital fail-safe hardware. ESD logic solvers use high-integrity, fault-tolerant architectures such as triple modular redundant, TMR, 2.3, or 102D. These platforms feature internal diagnostics, voting logic, and hot swap capabilities. All critical components, power supplies, processors, I/O modules are fully redundant and monitored continuously for integrity. Seamless but independent integration. While ESD systems communicate with the Distributed Control System (DCS) for monitoring, they remain functionally independent. Critical shutdown actions are executed through hardwired circuits to actuators, independent of DCS logic, ensuring that control failures cannot affect safety responses. Synchronized interlocks and action propagation. The ESD system maintains real-time connectivity with the fire and gas system, FGS, rotating equipment protection systems, and other safety-critical subsystems. Shutdown triggers from these systems are propagated across all relevant equipment in a coordinated, cascading logic using digital interlocks and SIL-rated safety relays or secure protocols. High-speed deterministic execution. Execution time from input detection to output actuation is optimized with scan cycles under 20 milliseconds. Safety-critical paths use deterministic communication buses, e.g. Profinet safety, EtherCAT safety, and pre-configured cause and effect matrices validated during commissioning. Its initiation modes and input sources. Automatic initiation. Based on real-time input from certified field devices, SIL-rated transmitters, pressure switches, vibration sensors, fire gas detectors, the system autonomously initiates shutdowns. Smart instruments communicate health and status continuously, enabling preemptive action before critical thresholds are crossed. Manual initiation. Manual emergency stops are triggered via hardwired latching push buttons, tactile key switches, or explosion-proof devices in field and control room locations. All manual initiators are monitored for integrity, e.g., line break detection, and are immune to DCS software interference. Remote and secure control. Remote shutdown capabilities are enabled through authenticated interfaces with secure protocols. Cyber-hardened edge gateways restrict access based on role, geofencing, and emergency override procedures. Overrides and reset logic. Controlled maintenance overrides. Overrides are restricted to SIL-verified maintenance override switches, MOS, and are only available under multi-tier approval through the DCS HMI under strict role-based security. Each override is logged and visually indicated with backlit status displays. Inputs tied to critical trip functions, e.g. manual ESDs, cannot be overridden. Automatic and manual reset architecture. Restarting after a shutdown event requires resolution of all initiating conditions. Local reset of field devices, e.g. SDVs, BDVs, and operator authorization at the control interface. Reset logic ensures that unacknowledged trips cannot be bypassed inadvertently. Diagnostics and testing. Real-time self-diagnostics. The system performs continuous diagnostics on sensors, logic processors, communication paths, and output actuators. Failures initiate alerts and automatic switchovers to redundant elements. Diagnostic health is visible on DCS HMIs and centralized safety dashboards. Automated proof testing. Built-in proof test functions simulate faults and verify trip responses without disrupting operations. Test reports are generated automatically and archived to satisfy regulatory and insurance audits. Remote validation tools. Engineers can validate shutdown logic, test inputs, outputs, and review diagnostics remotely via encrypted connections, reducing time and risk associated with field interventions. Compliance and cybersecurity. Standards-based safety management. The ESD system is designed in compliance with IEC C61511 lifecycle processes, including hazard and risk analysis, HRA, safety requirement specifications, SRS, safety instrumented function allocation, and safety integrity verification. Integrated cybersecurity measures. All networked components follow ISA IEC 62443 zones and conduit segmentation, intrusion detection, and anomaly logging. No ESD action can be initiated or disabled over unsecured or unvalidated paths. User interaction and operator interface. Dedicated ESD panels. In addition to visualization via DCS HMI, the ESD includes dedicated hardwired mimic panels with LED status, trip indication, and manual initiation switches. These are ergonomically located and continuously powered via UPS with battery backup. Contextual operator guidance. Upon ESD trigger, the operator interface displays a guided response checklist with real-time confirmation of valve positions, pressure levels, and downstream effects. System status is time-tagged and displayed in synchronized event viewers. Audit and forensics. Every trip, override, diagnostic alert, and manual intervention is logged in a tamper-proof sequence of events (SOE) recorder with millisecond timestamping and cross-system correlation. Historical analysis supports continuous improvement of shutdown logic and operator procedures. Through intelligent design, modern ESD systems not only ensure emergency protection, but also contribute to predictive safety management, digital transparency, and high system uptime in increasingly complex and automated process environments. Emergency Shutdown System Design Guidelines, Modernized Standards and Best Practices. Modern emergency shutdown ESD system design is grounded in the principles of safety integrity, diagnostic transparency, high availability, and cyber resilience. The system serves as the final protective layer in industrial automation and must perform flawlessly under all operating and fault conditions. The following design guidelines reflect the latest best practices in safety critical systems engineering. System architecture and redundancy, SIL3 certified logic solvers. The core logic processing unit shall be a 2V approved SIL3 rated platform with architecture such as 10U2D, 1 out of 2 with diagnostics, or TMR, triple modular redundant. Voting logic is implemented throughout the signal path, from input acquisition to final output execution, to ensure deterministic decision-making even in fault conditions. Modular, hot-swappable components. All I/O modules, processors, and power supplies must support live replacement and hot swapping without requiring system shutdown. This minimizes downtime and supports online maintenance in high-availability environments. Full input-output redundancy, ESD input signals, e.g. pressure, temperature, flow, and outputs, e.g. shutdown valves, blowdown valves, are designed with full redundancy. This includes dual transmitters on separate signal paths and redundant output drivers to critical actuators. Fail-safe logic philosophy. All safety logic is inherently fail-safe. Any loss of power, communication failure, signal open circuit, or diagnostic fault defaults to a safe plant condition, typically shutdown or isolation. De-energized to trip DT principle applies to all final elements. Diagnostics and health monitoring. Continuous loop integrity verification. Every I/O channel performs built-in diagnostics, including line break detection, short circuit identification, signal deviation monitoring, and power loop testing. Faults are flagged in real time and made available to operators and maintenance via dashboards and alerts. Device-level diagnostics, EDFD. Integration with smart field devices using protocols like HART, ProfiSafe, or Foundation Field Bus enables real-time health reporting from sensors and actuators. Predictive diagnostics are used to assess degradation trends and enable just-in-time maintenance. Centralized diagnostic dashboards. A unified dashboard consolidates the health status of all safety loops, logic solvers, communication links, and I/O modules. Traffic light indicators, fault counters, and action recommendations guide operators and maintenance engineers proactively. Configurability and safety logic execution, graphical safety logic development tools. Safety applications are configured using certified graphical development environments, IEC 61131-3 compliant, with enforced constraints to prevent programming errors. Logic blocks include pre-validated SIF templates, sequence controls, and override conditioning functions, change management, and version control. All configuration changes are tracked via automated versioning systems, requiring electronic sign-off, timestamping, and audit trail generation. Configuration rollback and simulation validation are mandatory before deployment. Simulation and emulation mode. Integrated simulation allows full testing of shutdown logic using digital twins or emulators without impacting live operations. This supports FAT, SAT, operator training, and control room rehearsals. Field implementation and safety devices, smart safety devices. All field devices connected to the ESD system, e.g., final control elements, sensors, shall be SIL rated, explosion proof, EXD or XIA, and certified for Zone 1 or Zone 2 as applicable. Where possible, smart diagnostics and event memory are enabled. Direct, hardwired field connections. All shutdown paths shall be hardwired from the ESD marshalling cabinets to final elements, e.g., SDVs, BDVs, relays. No critical signal shall pass through programmable logic in the DCS. The use of interposing relays is not permitted for safety-critical paths. Loop segregation and electrical isolation. Safety and control signals are physically segregated in wiring, cabinets, and terminals. Intrinsically safe, IS and non-IS wiring are routed through separate barriers with galvanic isolation and proper earth referencing. Pulse-tested output circuits. All outputs are equipped with pulse testing mechanisms to confirm valve coil integrity, wiring continuity, and solenoid functionality without actuating the valve. Failures are flagged immediately. Interface and visualization. Dedicated safety mimic panels. Physical mimic panels provide real-time visual feedback for ESD status and manual initiation. They include tactile push buttons, backlit indicators, and key switches, all hardwired to safety logic solvers. Digital cause and effect matrix implementation. All shutdown logic is derived from a digital cause and effect matrix validated during HAZOP SIL assessment. Any logic or I/O changes automatically update the matrix for traceability and audit compliance. Operator guidance and status visualization. Operator interfaces display real-time ESD statuses, active trips, overrides, and loop faults. Context-sensitive help and SOPs are displayed upon trip detection, guiding the operator through mitigation steps. Testing, proofing, and lifecycle compliance. Automated, partial stroke, and proof testing. Final elements, e.g., ESD valves, support online partial stroke testing and full proof testing intervals as per safety requirement specifications. All test results are logged and time-stamped for audit readiness. SIL verification and safety lifecycle management. Each safety instrumented function, CF, is documented with risk reduction targets, probability of failure on demand, PFD calculations, and periodic validation schedules. Safety lifecycle workflows are maintained using tools like Xilentia or 2V certified platforms. Remote commissioning and FAT. Virtual FAT capabilities enable remote witnessing, simulation of I/O, and validation of shutdown logic via digital twin environments. All logic downloads are digitally signed and verified against safety constraints. These modern ESD design guidelines ensure a balance between deterministic protection, operational transparency, system resilience, and compliance with global safety standards, positioning the ESD system as both a protective mechanism and a strategic enabler of safe, digitalized operations. Operator console and safety station design, modern integrated interface philosophy. In advanced process automation environments, the operator interface is the nerve center for real-time decision-making, supervision, and emergency response. Modern consoles and safety stations combine intuitive design, digital ergonomics, and resilient hardware to ensure operators are equipped to manage both routine and abnormal conditions. Integration of the Distributed Control System DCS, Emergency Shutdown System ESD, and Fire and Gas System FGS is seamless, yet each retains functional independence for safety compliance. Integrated Operator Console Design. High-performance visualization platforms. Operator consoles utilize ultra-wide 4K resolution multi-monitor displays or panoramic curved panels that allow full situational awareness across process units. Visualization software supports dynamic overlays of process parameters, digital twins, and fault propagation models. All displays are touch-capable and gesture-responsive, with optional voice control for hands-free operation. Ergonomic modular workstations. Consoles are height-adjustable, anti-glare, and thermally managed, built with ESD-safe materials. Layouts follow ISO 111064 ergonomic standards to reduce operator fatigue. Devices are mounted with cableless docks and articulated arms, enabling fast reconfiguration. Redundant Operator Workstations, OWS. Each OWS is configured in active-active pairs with real-time mirroring. In the event of failure, a seamless switch ensures uninterrupted control. These workstations run on industrial-grade computers or virtual thin clients connected to high-availability back-end servers. Advanced HMI capabilities. All HMIs offer multi-window as multi-unit and multi-domain operation. Contextual interface logic presents the most relevant data based on process state, alarm severity, and operator role. Functions like trend browsing, root cause tracing, and SOP retrieval are built in. Intelligent alarm interaction. While alarms are rationalized and prioritized, the interface shows system messages, safety interlocks, event sequencing, and status indicators in a layered color-coded format. Operators can filter, shelve, or escalate issues with just a few clicks and access real-time cause and effect diagnostics. Safety Console, ESD FGS hardwired interface. Dedicated Emergency Shutdown Console. A standalone hardwired ESD panel is positioned within immediate reach of the main operator console. This console includes manually actuated latching push buttons, key switches, and visual indicators for all critical ESD functions. It is powered by redundant UPS and designed for continuous operation even during power outages or DCS failure. Fail-safe manual initiation devices. Manual ESD triggers, typically mushroom head push buttons or pull-to-trip switches, are installed in field areas, control rooms, and near operator stations. All are hardwired directly to the ESD logic solver, ensuring trip reliability even under communication failure. LED-based mimic panels. FGS and ESD mimic panels display real-time status using LED matrices with zone-wise and device-wise clarity. LED color coding identifies gas detection, fire events, system faults, overrides, and manual bypasses. Panels also include push buttons for audible alert silencing and system acknowledgement. Integrated maintenance overrides. Maintenance override switches, MOS, are physically separated, backlit, and labeled. Activation requires pre-approved digital authorization through the DCS and manual enabling via a hardwired toggle. Once engaged, the override is indicated on both the panel and operator screen, with timestamped logs recorded. Functional integration and workflow continuity. Unified view across systems. Any authorized console can display DCS, ESD, or FGS screens with full user rights segmentation. Operators view process flows, shutdown sequences, fire maps, and gas dispersion models without changing workstations. Shared event viewers unify trip, fault, and operator action history across platforms. Role-based access control, RBAC. Operator actions are governed by role-specific access, e.g., field operator, panel operator, shift supervisor. Control transfers, remote interventions, or override commands require dual authentication and are tracked for compliance. Real-time collaboration tools. Integrated voice over IP, VoIP, chat messaging, and screen sharing allow operators to coordinate responses with field personnel or remote experts. Event replays and simulation tools support shift handover reviews and incident debriefs. Cybersecurity and availability. Isolated safety domains. Operator workstations that interface with safety systems, e.g., ESD, FGS, are configured with separate network zones and dedicated communication gateways. These zones follow ISA IEC 62443 defense in-depth principles. Redundant network paths. Operator console data is transmitted over dual redundant industrial Ethernet or fiber optic networks with automatic failover, ensuring continuous operation even under link degradation or switch failure. Disaster recovery readiness. In the event of catastrophic console failure, fallback stations, e.g. in the supervisor office or secondary CCR, provide instant continuity. All screen configurations and operator permissions replicate from secure cloud or on-premise backup. Augmented and remote console extensions. Remote monitoring stations. Supervisory staff can securely monitor process status, KPIs, and safety indicators from remote terminals or mobile tablets over encrypted channels. Read-only or restricted action modes prevent unintended interactions. Augmented reality, AR, overlay integration. Field technicians using AR headsets can project operator console data, such as valve positions or interlock status, onto live equipment views. Control room operators receive synchronized visual feeds for guided interventions. By combining physical robustness with digital intelligence, today's operator consoles and safety stations provide a unified, secure, and resilient interface environment. They empower operators not only to respond effectively during abnormal conditions, but to predict, prevent, and optimize across the full operational spectrum.